Day 68, page 272, rotational kinematics, problem 37. Over here in blue, I have the basic equation that the tangential velocity is equal to the radius times the rotational velocity. And if I rearrange that equation, this is the same equation rearranged. I have omega, the rotational velocity, is the tangential velocity divided by r. This is what I'm going to basically be using in this problem, because any two wheels, and I've labeled these because there's a lot of labels going on here. Wheel A is the bigger wheel here, or pulley, and then the smaller wheel B. But those are attached together, so they have the same rotational speed. Wheel A and wheel B, their rotational speed, omega A equals omega B. Same thing for C and D. Up here I've labeled them. The outer wheel C, the inner wheel D. They have the same rotational speed. The one thing that connects everything is the rope, once again, with like two gears stuck together, or two wheels touching each other, rubbing against each other, with a belt or a pulley or with gears, teeth. The tangential velocity of one wheel connected to another wheel is the same tangential velocity. So they have different rotational speeds, but two wheels, wheel B is connected to wheel D by that rope number 5. That rope number 5 will have the same linear speed everywhere, same tangential speed as it connects wheel C to wheel B. That's going to be a critical step in this process. So what I did is I started over on the left here. The hand is pulling down at 2 meters per second, but that's making the wheels A and B rotate at the same speeds. Wheel A and wheel B, same speeds. So the rotational speed is the tangential speed divided by the radius, which I have down here on the lower left, the tangential speed over the radius. So the tangential speed over the radius of wheel A equals the tangential velocity over the radius of wheel B. So I just plug in everything I know. I know the tangential speed, because I'm pulling down rope number 3 at a 2 meter per second. That's the tangential speed of that rope attached to pulley A, which has a radius of 24 centimeters, and the tangential speed of wheel B, which has a radius of 12 centimeters, is pretty easy. It's going to be half as big. It's going to have half the tangential speed because the circle is half as big, half the circumference. All right, so if the tangential speed of wheel B is 1 meter per second, that means the tangential speed of that rope number 5 connecting the two, going to point to wheel C, or pulley C, is 1 meter per second. So once I have that, then I can take the relationship once again, that the rotational speed is the tangential speed divided by r. So tangential speed of wheel C over the radius of wheel C equals the tangential speed of wheel D over the radius of wheel D. And I know everything. I know the tangential speed now of wheel C. I just got that above. The radius of wheel C. We're looking for the tangential velocity of wheel D, which will be pulling up the money bag, over its radius, 15 centimeters. So it's just a matter of plugging that in, and you come up with 0.75 meters per second that the money bag will go up if you pull down with a speed of 2 meters per second.